All right, let's go ahead and start up here. Okay, so back into chapter 8. Okay. And one thing I wanted to look at before we got back into the reactions. Remember, we've been looking at addition reactions to double bonds, and want to consider two different types of addition reactions. Okay, so if you had a double bond and we're reacting with some XY, okay, there's two ways that XY can add across that double bond. Okay. See the differences there? One way is to have them add on the same side where the double bond was. And so we call that Syn Addition. If they add on opposite sides where the double bond was, we call that Anti-Addition. Okay? So these are the two types of addition reactions that we want to keep in mind. We haven't really specified whether a reaction can go either way, but we're going to see that today. Letter in there. Okay. So let's keep these two things in mind, and I'll be specifying reactions as one or the other as we go through this, okay? So let's go back to the reaction we were looking at. Which was the hydrogenation reaction. Okay. And remember, in the hydrogenation, we were reacting the double bond with BH3 borane, then hydrogen peroxide and OH minus. Okay. So remember what kind of product you get with this hydroboration reaction. We got an alcohol. What kind of alcohol? A non-Markovnikov alcohol. Okay, so that was one of the key properties of the reaction. So that meant that the alcohol went where? On the less substituted carbon of the double bond. Okay, so if we were doing the reaction from what we learned last week, this is what we got here. But now there's one extra thing we need to throw in the mix. What kind of addition is it? And it goes on by anti-addition. Okay? So you got to also remember in these reactions we're doing, whether it's anti or syn addition. Okay? So this is adding on anti, and if it adds on anti, this is going to display itself in the ring if we had a double bond in the ring. And the way it will display itself is what? Cis or trans. It's anti. It'll be trans. Okay? So anti-addition in rings will show up as trans. So I can't leave the molecule like this. I've got to show you the trans product. Like that. Okay. If I had done the same reaction without a methyl group there, you know, then I would have just got regular cyclopentanol, and there's nothing to designate it as trans, so that's the only thing I get. Okay, so I'll see the trans if I have a group on the double bond. They're going to be right in the middle of that. Sit back. Okay, any questions on that? Okay. All right, so that's the hydroboration. Okay. Let's go on to our next reaction. Our next reaction, we're going to react our double bond with X2. In organic chemistry, what does the X generally stand for? A halogen. Okay? So the two that we're going to focus on are bromine or chlorine, Br2 or Cl2. All right, so this will be a little involved, so make sure you stay with me here. So let's write out a model. The model is if I have a double bond and I react with my dihalogen, what do I get? I get my halogens adding across the double bond. But they add this way here. What way are they adding? Anti-addition. Okay. And so we get a vicinal dihalide. Anybody remember what vicinal meant?
The opposite of geminal.
Okay. So what does that mean?
Geminal, same side, vicinal, opposite side. Of the double bond.
Okay, vicinal means neighbor. Neighbor. Do you have a neighbor?
Yeah.
Right there. Okay. So vicinal dihalide means the two halogens are on neighboring carbons, and they end up anti to each other. Okay? So let's take a look at this reaction using a real molecule. So let's draw out bromine for this case. So how's this reaction going to work? Well, if you look, we have a double bond. And again, when I have the double bond, I draw a gigantic set of lone pair on it. Okay. Now, how is that lone pair going to react with the bromine? Well, what happens is the bromine is polarizable enough that it can have a shift real quickly of electrons. And so at a real quick shift, it can set up a dipole difference like that, even though they're the same atoms. Okay, this is what we call an instantaneous dipole. So at any one moment, when these two collide, then the lone pair can attack and kick off that bromine. Okay. So either one of these carbons will grab that bromine so let's choose the left-hand carbon, and that would give the right-hand carbon what? A positive charge. Okay? So remember, one side gets the atom, the other side gets a positive charge. Okay. Well, what happens next is something a little bit new to us. This bromine there has some sets of lone pair, and what it does is it senses the neighboring positive charge, and it goes ahead and attacks it. See that? So that it forms this three-membered ring within that ring. See that? This is what's called the bromonium ion. Okay? So the bromonium ion is simply a three-membered ring with a bromine that has the positive charge on it. Okay? And this bromine is sticking up on the side of the ring. So this ring, you can imagine, is flat like this yardstick, and that three-membered ring is sticking up like that, okay? So it's not coming out parallel to it, it's sticking up on the ring, okay? Now, this bromonium ion, do you expect it to be very stable? No. Why? It's a three-membered ring. Three-membered rings are very unstable. So this thing starts to break. And as it starts to break, that carbon, where it starts to break, forms a partial positive charge. And so the Br minus that left over here can now attack that positive charge. But note how it attacks that delta plus here. It attacks it where? On the opposite side where this Br plus is here. Okay? So we have an anti-attack. Okay? So the top side attack is shielded by that Br plus. So it can only attack on the bottom side. So the result is that the bromines end up anti to each other or trans to each other. So we get our trans product. Okay? And you can redraw this in a little neater way to show that they are trans, like that. Okay, any questions on that? We'll do another one, give you some more practice. I guess that was pretty easy to understand. Okay, let's do another one. Suppose we took this alkene and reacted with Cl2 here. Okay. Let's see if we can follow this mechanism. So again, if I have a double bond, I draw in a gigantic set of lone pair tacks. Kicks off the chlorine. Okay. So chlorine adds to the less substituted so that the more substituted gets the positive. Then the neighbor attacks. So here we form that three-membered ring again. Which again is not very stable. It wants to start breaking, but which side will want to start breaking more? This right side or this left side? Why the left side? Okay. Forms the left, then I start forming a secondary carbocation. If it did here, that'd be primary, it'd be less stable. So you're right, the left side will start breaking so that my second chlorine attacks the top side. And so we get this product here. Okay. So note, it's not a ring, so I don't have to show any cis or trans. But in the mechanism, I see that, yes, it did do the anti-addition. Okay. So make a note of it. When we draw this dotted line for this bond, that means that it means that it's partially breaking. Okay? Versus a bond that's solid means it's not breaking at all. So it's kind of like a transition state. Okay. Any questions on that? Hopefully that second example. Okay. One of the things when we do the reaction with bromine, Br2 is a deep red color, almost looks like blood. Okay. Did you ever see blood? Well, here, if you do this reaction, with bromine, it would turn colorless on the other side. Okay. So what's the big deal about that? Okay. Well, the big deal is suppose you were given some molecule that was unknown to you. You didn't know what it was. But your boss says to you, I want to find out if that is an alkene. What could you real quickly do? Grab a jar of Br2, take your pipette, get a couple drops, put it into your unknown. If that what turned colorless, then you knew it had a carbon-carbon double bond. If it stayed red, what would that mean? It doesn't have a carbon-carbon double bond. It's not an alkene. Okay? So this is a nice qualitative test that you can use in the lab. Any questions on that? Okay, well, let's stick with this reaction, but do something, just a little tweaking to it. And in this tweaking, what we're going to look at is what's called the halohydrin formation. The halohydrin formation. Okay? So what's going on here? Okay. Let's look at this molecule back with 1-methyl cyclopentene, and let's react it with bromine. And now we're going to throw in some water. Okay? So the water's going to throw this off a little bit. Okay? What happens is that, let me draw the resulting product for you. Get something like this. Okay, we'll look at the mechanism in a second. Okay, so let's talk about this product for a second here. First of all, it's called a halohydrin because we've added a halogen and water. Remember when we add water to a molecule, that always makes an alcohol, okay? So it's called a hydrin because we've added water. So halohydrin is where that name is. The second characteristic about this is that X and OH end up trans to each other. Okay? The X in this case is the bromine. Okay? And what's the third characteristic about it? The OH ends up on the more substituted carbon where the double bond is. Okay? So in this case, it ended up here, and the bromine was on the less substituted. Okay? So those are the three characteristics of the product that you want to remember. Okay? Now, let's see how that forms. Okay, so let's look at the mechanism. So, again, I have a lone pair that will attack bromine and kick the other one off. Okay, so the bromine adds to the less substituted, right? So that the more substituted gets the positive charge. Okay, so here I get a tertiary instead of a secondary carbocation. Okay, so that's why we're going to see the OH ending up on the more substituted carbon. So what happens in the next step? The bromine has its lone pair, so it's going to form that three-membered ring again. There. And now the more substituted side will start to break so that my partial charge forms on the more substituted carbon. Then in the next step, instead of Br minus adding on, the water is going to add on, and it will come in anti to the top bromine. Now that water is added on. And again, you have oxygen with 3 bonds, so it has a positive charge. So that makes either hydrogen what? Acidic. So I can remove it. With that Br minus formed over here. And we get our halohydrin. Okay, it's just a little twist with that reaction. Any questions on that reaction? Question?
In the example that we did before that, the skill, in the last mechanism, was attached to the molecule. So with this one, the OH replaces the second BR?
That's right.
Okay.
And if you did it with the chlorine, it would replace the second chlorine.
Okay.
Okay? So let's just do another quick example, make sure we're on the same page there. Let's see if you can draw the product for that. Don't draw the mechanism, just draw the product. Okay. So what would happen here? Where would the chlorine end up?
Put a one substitute with carbon
And the OH on the more substitute. Any questions on how we did that? Raise your hand. I maybe got that one right. About halfway. Any questions? Yeah.
You said because it's not a ring, it doesn't matter whether it's not.
Exactly. Since it's not a ring, you don't have to show cis and trans. Only on the ring do you have to show cis and trans. Okay, so make sure you practice these things. Okay? You have some good practice problems, 8-21, 8-22. Okay, so make sure you can handle those. Question?
What about the other seal? The seal.
It took off the acidic hydrogen, so it formed HCl is a byproduct. Okay, let's move on to the next reaction, the last one for today. This one is called the hydrogenation reaction. What do you think we're going to add this time? Hydrogen. See it in the name there? Okay. Finally you got it. Okay, good for you. Okay, so here, here's our model where we have a carbon-carbon double bond. This time we're going to react with H2, that's our hydrogen. You never get hydrogen as single atoms, it always comes as the diatomic. And we're going to use some kind of metal like platinum, palladium, or nickel. Okay, so either one of those three will work as a metal catalyst. If you don't use any of those, the reaction will not work. And what you get as a result is this product here. So the two hydrogens add across the double bond. How did they add across? Syn addition. Okay, so here's our first example of Syn addition. Okay, you might have been wondering, are we going to see any syns? Okay. All right, so let's look at an example of this. Suppose we had propene and reacted with H2. What would you get? Okay, you get those two hydrogen atoms adding across the double bond. So that if you shrink wrap it, we got propane. Okay, so you go from propene to propane. Okay. Let's talk about some characteristics of the reaction. Okay. Give me some words that describe what we did. And going from here to there. Any differences? Okay, we added the hydrogens. Anything else you could say? You got rid of the double bond. So what other wording could you use for that? Equal. Okay, so here this was unsaturated. So we saturated the molecule with what? Hydrogens. Remember that?
Where's this CH2, the H,
Yeah, so these two hydrogens make a CH2, and these make a CH3.
oh, it's in the name. Oh.
Yeah, yeah. Okay. So this is an example of a saturation reaction. Okay? Remember, this had 1 degree of unsaturation. When you saturate it, it has 0 degrees of unsaturation. 0 degrees. Okay. This is a very popular reaction, okay? In industry, what we do, one of the biggest ways this is used is when you take butter or lard or some kind of solid animal fat. Those tend to have very long chains of double bonds in them. And those double bonds help to make the fat a solid. Okay, so you know butter is a solid. Well, when you hydrogenate it with hydrogen, it gets rid of all these double bonds to make it fully saturated. And so it's no longer a solid, but becomes what? An oil. Okay, so that's, you know, you buy your vegetable oil. That's how they make vegetable oil. Okay, they make vegetable oil from butters and so on. And so it becomes saturated, or what you hear polysaturated versus polyunsaturated. Okay. So this process of hydrogenation is used a lot. Okay. So you got to be careful. Your body likes double bonds because it can react with them. If it gets too saturated, your body can't break those down, and it gets confused. And if you build up too much saturated fats within your body, it start causing cancer and stuff like that. Okay. So you gotta be careful of your diet. Make sure you don't eat too many French fries, fried chicken. Okay. Get too much of that oil in your body can't handle it. Okay. So make sure you eat that stuff in moderation. Okay. All right, so we'll stop here for today. Again, we're looking at our next exam next Wednesday after Easter. I'm sorry?